Hello. Today we are writing a contest. Think Cell round 1. I am quite prepared. I have my nice file. It should output 000 now. Yes. Okay, let's go. Maximize the score. There are 2 positive integers. We have a 1-player game. We choose 2 integers x and y, add minimum and erase x and y. We need to find the maximum final score. It's such an interesting problem. Two to three. What's wrong? What's happening? Ah, I'm nervous maybe. Again 000. Nice. Why am I so nervous? Okay, fine. Pi divides pj and pi plus 1 divides pj plus 1. What's happening? Ah, okay. Okay, this is a constructive problem. Okay, so the easiest thing would be if we have something like, so if pi is greater than pj, then pi plus 1 should be less than pj plus 1. It would be the best thing. But I'm not sure it's possible. Or is it possible? Okay, maybe it's true for... for 1n, 2n minus 1, etc. So here we have IRN. So we put A1 equals n minus 1. And for Okay, there are two cases actually. No, there are not two cases. We simply say that if I is odd, then AI equals AI minus 2 minus 1, else AI equals AI minus 2 plus 1. And return A. Okay, almost, but no. So we need that if some element is greater than some other element, then the next one is less than the next one. So is it true? Okay, let's look at 10, for example. So if you have an element which is if there is an element which is less than the other element, like this, then the next one should be greater. Yeah? If they are of different parities, it's obvious, and if they are of same parities, it's also obvious. Okay, I think it should be fine. Yes, it should be fine. Yes, it should be fine. Problem C. So we have a set. We insert AI plus I into S, and we delete AI from A. Find the lexicographically largest B that stack can make. Okay, why don't we just want to take all the biggest elements? Because if we take two equal elements, it's actually not the best thing we could do. Yeah, so basically the problem looks like this. Oh no. Yeah, basically we have some, let's add the index to each number. So we have like a1 plus 1, a2 plus 2, etc. an plus n. And let's call them mu a's. So we can take an element and then everything to the right of it is decremented. Okay? Okay, it seems like we always take the maximum. Okay, I think I understand what to do, and it's not very hard. So VIA. So what do we do here? First things first, we add I+1 to each element. Then we sort it. And then we go through this array. So if I and AI is at least AI minus 1, then AI minus 1 equals AI minus 1. And return A. Two, 3. 3, 2. What? Three, 2, this thing, 11, 7, 6. Okay. It's a simple greedy algorithm. Thank you. So I'm now a trusted participant. And I. Okay. So what do we need to solve now? I don't know. I'm 12th? Because I didn't prove it and everybody else for some reason struggled to prove it. For a binary pattern and a binary string Q, so we have a binary string P and a binary string Q. Both of length M. Q is called P good if for every I there exist indices L and R such that LR is a segment that contains I and PI is a mode of the string Q. For a pattern P, let f of P be the minimum possible number of ones in a P-good binary string. Well, it's not an easy problem. At least I feel like it. Okay, we have a pattern. For example, if we have all zeros, then it's clearly we have to take if it's all zeros, we clearly have to take like what? We want to find the minimum possible number of ones. Yes. Okay, we don't have any. We don't put any ones. This is easy. But if we have all ones, what do we want to put as Q? It seems like we want to put a middle third of ones into Q. So if we have some element here, we still can take this segment. And in this segment, 1 is a mode. Can we take less than 1/3? I'm not sure, but I don't know how to prove it. We can just take... Also, another possible way is to just write 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, etc. If we use this string, it also, for each element, there is nearby 1. Is it true that just we have to write a string in which for each one there is 1 somewhere here? Is it true? If so, then it's a simple DP. Yeah, if so, it's a simple DP. And in D2, what do we have in D2? Ah, problem E is solved. Well, no, I will solve problem D, I believe. Okay, let's start with the easier problem. The sum of n squared over all these cases does not exceed 10 to the 4th. And here, n does not exceed 10 to the 6th. Okay, let's solve it. So we read a binary string. So we say that bi equals ai equals 1. Then we find answer, which is maybe long. Okay, now let's solve it in a stupid way. So for that, what do we do for that? We need to store the number of ways if we have last one and last but one or one. So ll no one ll like okay, a0 equals this, a1 equals this, and a2 equals 0. Okay, then we go through what? 346? Ah, okay. Well, here we have to go through all possible pairs of indices. Okay, and we have VBB of size j minus I. Okay, we have constructed BK. Now let's have this one. What's happening? Ah, okay. So we go through all symbols. And if BK is true, then we have to use one here on the or the previous turn or the next turn. Okay, for each string we have two answers. For prefix of size I, we have an answer when we have to put one here, when we have to put one here, and when we don't. When we have to put one here, and when we put one here and when we put 0 here. Okay, there are two cases. Okay, when we put 0 here, it's 0. And when we put 1 here, it's this big number. Okay, so assuming that we have calculated it for prefix of size k, now we have, of length k. Now we have the kth symbol here, and we need to calculate it for a prefix of length k plus 1. So if we have a 1 here, then we have to no, it's not true. So, okay, this is B, and this is what we put, like Q. Okay, let's solve like this. So, okay, we have a prefix of length Q. And let's consider cases that we have a 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1. So A0, A1, A2, A3. Okay, it should be easy. Well, so again, let's look at this symbol. So if we have, so this is calculated. If we have 0 here, let's also say that bool pref equals false. So this is pref. So if this is 0, then if we want to use 0, 0, Okay, let's consider 4 cases. So if this is 0 and this is 0, and then in the end we will say that previous equals BK. So okay, if these are both zeros, then we can put here whatever we want. It doesn't matter. We can put here 0 easily. We can put here 1, it doesn't matter. So we can say that so here we say that A0 equals B0, A1 equals B1, A2 equals B2, A3 equals B3. So if we want to have 0, 0, then we can use either 0, 0 or 1, 0. So B0 is minimum of A0, A2, B1 is minimum of A0 and 2 plus 1, B2 is minimum of A1 and A3, and B3 is minimum of A1 and B3, A3 plus 1. Okay, else if not, I don't know how to write such dynamics, sorry. Okay, let's assume that now it is 0, but here we had 1. In this case, if we had 0, 0, then we definitely have to take 1. Yes, so B0 is definitely A2. However, everything else is same. Yes, so we just need to put 1 sometimes. Yes. So the next case is BK, but not PRV. So BK but not PRV means that we have 1 but 0 here. Okay, this means that we can do whatever we want. Actually, we can do whatever we want. So this 1 doesn't restrict us because we still can put 1 here. So actually, it doesn't matter what is here. Only PRV matters. Yes? Yes, I think yes. Okay, and in the end, if PRV so if PRV, then we can only take B1, B2 equals minimum of A1 and minimum of A2 and A3. But if PRV, if not PRV, we can also take A0. And then ans plus equals corans. And then return ans. This took an enormous amount of time, but we finished. I hope. No, we didn't finish. What is n? 2? Yes. No, it was the wrong problem. I will just get an Editorial. Okay, now we need to somehow do it faster than that. But I don't know how. I really don't know how to do it. So now the sum of all n's, maybe we can solve E? Maybe it's easier. Let's look at it. So let's create a new file, which is called temporary.txt, and here we will put our solution. Yeah, it still compiles. Yeah, kinda. So we have an array of length n such that ai equals I. He'll select a positive integer k. He'll select a subsequence of length 2k plus 1 and delete the first k elements of S from A and the last k elements of S from A. He will just remove 2k elements between which there is at least one element. So we have, again, we have an array. Here he selects a positive integer k. He removes k first element of S and k last element of S. Well, what do we have in the end? In the end, sorry. Okay, so for example, k equals 2, I don't know. Then he can remove first two elements and last two elements of something, and here should be at least one element. Okay, in the end, let's look at the final element of this. The last element among all these operations. Here it is. Actually, is it true that if we can get something via k operations? No. Yes, actually see. So let's look at the following operation. We just take two elements between which there is at least one element, and we remove these two elements. I want to prove that actually any operation, any k such operations is just one operation where you take the subsequence of k and subsequence of k and remove both. Oh, no, actually, no, it's not true. Because there is this example. You can remove all black elements in 2 operations. But you cannot remove an in 1 operation because this and this does not have an element between them. Well, it's not wonderful. It's a disastrous problem. I think we need to go back to problem D2. But how do they solve problem E in 14 minutes? I don't know. Maybe they know something. Ah. Ah. AI equals I for all i's. Okay. So actually it is a permutation. Well, it's a bit better. So this means that we don't have any equal elements. Okay, let's think. So let's think. So assume that we have some k. Then obviously the length of this array is n minus alpha k for some alpha. But is it possible to get any array of size of this size? No, as we have seen, if we have 6 elements, we cannot end up with 2, 5. We cannot end up with 2, 5 if k equals 2. Because it is impossible. Yeah, that's not exactly possible. Okay, what is possible to get? Okay, let's start with the easier question. If we have n elements, 1 to n, and in k equals 1, what can we get? We can remove any pair of elements between which there is one more element. So obviously we cannot... What we cannot? I think maybe it is impossible to what? Okay, first of all, if so let's consider, so the number of elements is 2m, removed elements is 2m for some m. So let's consider first m elements and the last m elements removed. If here and here these 2 removed elements are neighboring, if they are not neighboring, then it is easy. We just have these pairs and that's it. If this is not the case, then they were removed. Well, then it's not what happened. Okay, let's find the rightmost not removed element here and the leftmost not removed element here. So what do we have? We have like two removed elements. Here we have A elements, here we have C elements, and here we have two M minus A minus C elements. Yeah? Then it is possible if 2M minus A minus C is at least at most A plus C. So A plus C is at least M. So we need to find two elements such that at least half of them is here or here. Yeah? Yes, I think it's true. So what about... Is it true? Ah, okay, yes, it is true. So now we have something more interesting. We have k is greater than 1. In this case, again, let's look at the first half of the removed elements and the last half of the removed elements. So if here we have an element, then it is always possible. If there is no such element, then we need to find the nearest element such that this is divisible by k, and here such nearest element that this is divisible by k, not removed element, non-removed element. And then again these elements should be at least half of the total. Correct? Or not. For example, let's consider this test case. Here we have removed elements 1, 3, 4, 6, and elements 2 and 5 are not removed. And 1 plus 6 is at least half of all elements. Well, but how to calculate it? I don't know. I don't know how to calculate it. Well, it seems like we need to choose some elements which number is divisible by k. What? No, it doesn't seem easy. So let's try to solve D2 maybe. Okay, let's postpone problem E. Again, problem D2. So we have some sort of segment. For each segment, we need to calculate this strange sum. So, okay, let's... So for P... So for each segment of B of this size, let's look at P of this size. And there are two cases. If we have a 1 here... No, we need 4 cases actually. So when we know this digit, it is either already satisfied by these two or not. And even if it is, we don't know if this one or this one. And it is important because it depends whether we can put here 0 or 1 or not. So it's not easy. It's not that easy. Well, but how to calculate it for all possible numbers? Maybe there's some sort of greedy approach. Yeah, there should be some greedy approach. Yeah? So yeah, if I have some binary string, if I have a 1, I just try to put my 1 here. Yeah? Yes, I just try to put my 1 here to the rightmost position. When I have the next one, if it is already satisfied, I am happy with that. Otherwise, I put 1 again here. Yeah. Okay, yes, I see what to do. I understand. So. Let's go through all digits. So let's store. So let's assume that we have considered I digits of my array A. This means that I already have I strings, which start here, start here, start here, and start here. For each of them, let's store its type. Its type is what are last 2 digits of this string. So 0, 0, 0, 1, 1, 0, and or 1, 1. Okay, for each of them, I will understand how I want to continue this. Do I ever want to put 1, 1? I think no. I think no. So if I put this 1, this means that I had a 1 here. This means that I never want to put 1 here, because I could put it here. Yes, I can only have 0, 0, 0, 1, or 1, 0, I think. So it is A0, A1, or A2. So, okay, I have I strings, which start here. Now I have my new digit. Okay? I have several strings which started before this prefix. Here, here, here. Okay, I have a new string which started here. Okay. First of all, since it started here, okay, let's again take bool pref equals false, and in the end here we will say that prv equals AI. So we have something. Now we have a new... Okay, let's consider the easier case when it is 0. When it is 0, first of all, let's consider all strings which start here, which... so if a string starts here, I definitely can just increment a0, 0, I think. So plus plus a0. Yeah, because the string had 0, 0 here. Okay. Now, if I have a 0, if I have my previous digit, I do it in the end, I think. I do it afterwards. So if PRV, then if I had 0, 0 or 1, 0, or if I had 0, 0, then I definitely have to put 1. But if I had 0, 1 or 1, 0, then I don't have to put 1, and I put 0. So if PRV, then I say that int. So if PRV, then B0 equals A2, B2 equals A1, and B1 equals A0. So this is some permutation. Also, for each string which started there, if I have a 1 here, then it is like increasing. So how many strings contain this one? Yeah, how many strings contain this one? So this one is contained in each string which starts, which was 0, 0 string, and which ended to the right of this place. So it should have ended here. So how many symbols are there? So if this is I, then there are n minus I symbols. Okay, this is how many ones are there. Otherwise, so let's assume that we have a 0. The previous symbol is 0. Then if we have 0, 0, it's 4. Then we can always take 0, I think, yeah? So we can say that B0 is A0 plus A2, and B1 equals, let me think, b1 equals 0 and b2 equals a1. And ans is not incremented. After that, we say a0 equals b0, a1 equals b1, a2 equals b2. But there is a catch. The catch is what if the string ends exactly here? So there are several strings which end exactly here. And the problem with that is if a string ends exactly here, then even if this bit is 1 and we had 0, 0, we have to put 1 here. So if 0, 0 or 1, 0. Yeah, so it is this case. So if ai, then we also have to say that answer plus equals what? Answer plus equals a0 plus a2 always. Okay, now we have traversed forward and we have a 0, 0 here. And here we write that we return ans. Also in the end we also have to do the same thing, I think. No, we don't have to do it. Okay, let's first check this one. Almost, but no. It said that it is 0. Yeah, I think... What? Houston, we have a problem. I don't understand what to do with this A0. Okay, maybe I will need to write +1 here. Now this is too big. And I don't know how to check it. We can, in principle, make a stress, although I think it is very bad that we are making a stress here. Okay, whatever. I'm not a proud bird. Okay, it found the test 1-1. Let's look at the test 1-1. So we say that the answer is 4. Yeah, but the answer is definitely not 4. It is 3, I think, yeah? Yeah, the correct answer is 3. Let's think how it is 4. Okay, we have A0, A1, A2, B0, B1, B2. Okay, answer should be 1 right now, yes. Mm-hmm. Okay, let's go again. So we have a PRV. So we have to... What? Answer plus equals 2 happened. It was 1. Come again, please. What happened? Why is it 2? What? Ah, we shouldn't consider the string which ends exactly here, I think. Yeah, we shouldn't consider the string which ends exactly here. That's the problem. Okay, now it's still too little. I hate it. I'm already starting to hate it because we're spending a lot of time on one test. Let's continue with the stress. Now it's 1-0. Okay, what's the answer for 1-0? Okay, the correct answer is 1. No, our answer is 1. But the correct answer is 2. Okay, let's fix our answer 1. Okay, let's again jump here. No. No, we don't need the stress right now. Okay. So we have an answer of 1. Hmm. Maybe we need to put a 1 here. Although it sounds really strange. No, I don't think we need to put a 1 here. So let's look at this string. So we have 1, and this is one string, 0. Then we have a next 0, and here we will have to put 1. But when do we calculate it? We'll calculate it when we have 0, 0 here, so we have to put 1. And we always have to put it here. We always have to put it here. Yeah, so we always have to put it here. However, if AI, okay, let's fix something. So what happens if AI? If AI, so we just want to fix the answer when the string ends exactly at ith symbol. Why do we need to fix that? Because if we have AI, we expect to put 1 here. We expect to put 1 here. Okay, I think it depends on pref. Okay, so first of all, if AI, then we definitely have to increase answer just because of this one string which starts and ends here. Okay, but if PRV, yeah, then also we have this one. And in this case, yeah, in this case, we already put 1 here. So we only need to put 1 here. Yeah, so we only need to put 1 in the case of A2. Otherwise, if we have a 0 in the end, so we have 0, 1, then we need to put 1 here. No, we need to put it always. We need to put it here and here, yes. So 0, 0 and 1, 0. Five, 5, 6. Oh my god. It's even worse. Just 0 is incorrect. Extraordinary. I need to remove this one because, yeah. Okay, so if we have a stress, it doesn't find anything. Yes, it doesn't find anything. The answer is correct. Let's submit it. Okay. We still have a lot of problems, unfortunately. Most of them I don't know how to solve. So problem E. Maybe problem F is better, but I guess no. Not really. So we need to find out how many ways are there to choose, for example, exactly. So to choose several elements, which number is divisible by k. Okay, first of all, there are ways where we choose number of elements which is divisible by 2k, and the center element is vacant. So how many ways are there? So we need to find the number of ways to choose several elements such that the central two of them are not adjacent. Okay, this is easy. We can just remove a fake element, and when we choose, we then add this fake element here. So this is easy. This is something like choose from n elements to k l elements, but since we have also a fake element, n minus 1 here. Okay, this sounds fine, but also we have several ways where there is no such fake element. Okay, this is hard. Also the number of elements should not be, isn't forced to be divisible by k, I think. Yeah, because it just should be like this number of elements is plus this number of elements is at least this number of elements. Why is that? Because for example, we can fix this residue by taking several elements here and then several elements here. Yes? Yeah, it makes sense. We need to take several elements here and then several elements here. For example, if we have 3, yeah, we can have 2 here and 2 here. And 2 here. Then we firstly remove... No, 3. So, for example, 4 here, 4 here, and 1 here, I don't know. Or maybe, or even, for example, 4. Okay, 7 here. It should be even fine with 7. So I take 3 elements here, 1 element here, and 2 elements here. Then here we take 3 elements here, 1 element here, and 2 elements here. And this doesn't work again. This doesn't work because the number of elements is not divisible by 2k, so it should be divisible by 6. Okay, let's consider some case when it is divisible by 6. For example, 4 elements here, then 7 elements here. 4 plus 7 is 11. So it needs to be divisible by 6, so we need to add 7 more. We added them here. So now I have the following: 3 here and 2 here, 3 here, 3 here, and like this, and finally 3 here and 3 here. So the puzzle is solved. The puzzle is solved here. Okay, so essentially, what do we need to do? First of all, let's glue up these two elements together. So now we need to choose KL minus 1 elements from N minus 1 elements. Okay? And the next issue is that we need to somehow guarantee that we have these two elements. Okay, this is really what I don't understand. Or even two KL minus 1 elements. So we simply need to have in this sequence 2 elements. Okay, let's consider all sequences and then we subtract the bad ones. What is the bad sequence? A bad sequence is a sequence which covers not only this element, but it covers in total KL elements. And if it covers KL elements, then KL plus 1 elements at least. If it covers at least KL plus 1 elements, then it is kinda bad. So this is like a segment of KL plus 1 elements together. So okay, let's think. What does it look like? Okay, how does it look like? So okay, all sequences, all good sequences equals with middle element and with plus without it. Now let's take those with middle element. Then we need to choose. So if there were no middle element, then we would just need to choose from our N element 2 KL elements. Yes, 2 KL elements, we need to choose them. Okay. From N elements, we need to choose 2 KL. However, we may assume that the middle one is... After the middle one, there is one fake element, so it looks like this. So now we need to calculate the number of ways to do it without the middle element. In this case, we can glue up these 2 middle elements and now assume that we are choosing N from N-2 elements 2 KL-1 elements. Okay, we can take all of them, but we need to subtract the number of ways in which there is a segment, a long segment. Okay, so let's... So this element is contained in a long segment. Yeah, so before the gluing up, it was of length KL plus 1. So after the gluing, it was of in a segment of size KL, at least KL. Then let's take the rightmost KL elements in this segment, and let's just glue them up into one element. And now we have two cases. Either this segment is touching the right border or not. Okay, let's consider two cases: when it touches the right border or not, or when it does not touch. When it touches the right border, okay, for now, let's glue these KL elements. So now we have minus KL plus 1. So we have this number of choices. However, if we said that this segment always touches the right side, then we don't have a choice in terms of this last segment. We have to take like this. Okay, the other case is if it does not touch the right side, but then we can glue it again with this new element. So it is like n minus k l minus 1 and kl. And in total, this is n minus kl over kl. So still, we just choose several elements. That is strange. That is strange because I don't know which of them is glued up. I really don't know which one is glued. Yeah, I don't know which one is a glue element. I believe we need to somehow color it, for example, or something. Okay, in this case, it is obvious which one is the chosen element, and in this case, we have to multiply it by KL because we need to highlight this element. So this is the formula. This is the formula. To be honest with you guys, it is not a lovely formula. So we read T, we read N. And we simply print the answer modulo this number. So we don't need stress for now. Find ans is one int. Is it one int? No, it's not one int, it's vector of ints. Okay. So first of all, let's calculate these answers for all numbers KL. Simply. Yeah, so for int ans of size n over 2, I think. n minus 1 over 2. Okay, let's say const int k equals n plus 1 over 2. Then we take here k, which means that we take at most n minus 1 over 2. And here we say that answer KL is difference of choose from n minus 1 to KL minus 1 and sum of choose n minus KL minus 1 choose KL minus 1 and product of choose the same thing but just KL and KL. And then we need to write modulo m, I think, everywhere. Okay, let's write it everywhere. Yes? What is m actually? Yes, m is what I supposed it to. Ah, because I have here ras. Okay. And then we need to go through all. Okay, I think let's not. Actually, it doesn't matter. Vi ans of size k minus 1. So we need to fill ans I minus 1. Something like this. Well, let's check. It's a bit worse than I thought. It's quite a bit worse than I thought. What are you talking about? So n is 3, k is 2. So answer should be of size 1. Ah. And now it's 0, 0, 0, 0, 0, 0. Let's look into this solution. So first of all, what are the advances? Zero and 0. Who would think? Why is that? Okay, KL equals 1. Okay, this is 1. This is also 1, so this is 2. And this is 2. Ah, we also need to add... So, okay, this is total is definitely choose of n, choose 2kl from n. One, 3, 1? I am feeling sad a bit. So there are 2 ways to get an answer. Either we can take 0 elements always. We can always take 0 elements. So we can easily say that it is 1 initially because we didn't take any elements. But still, this 8 should be 10. Okay, let's look into the case when it is 5. Okay, 1, 2, 3, 4, 5. They're claiming that there are 10 arrays. There are 10 possible arrays. So there is 1. What can we take? Okay, we can either take nothing, or we can take 1 and 3, for example, 1 and 4, 1 and 5, 2 and 4, 2 and 5, 3 and 5, and also 1, 2, 4, 5. Okay, I have an answer of 8. How I will get in 10? Sorry, what? So I equals 1. So we have numbers from 1 to 5. We have numbers from 1 to 5. We remove. We choose 3 elements. And remove 1 minimum and 1 maximum. Stack wonders how many arrays A can we end up with for each k. Okay, you're trying to tell me that we can actually get this and this, or this, or this and this. So we can actually end up with this element. Okay, I agree with you, but this is counted in my, this should be counted at least in my answer. So n equals 5. KL. Okay, let's look at all divans and see what I don't like. So I don't like that in total this is, so this is 6 plus 1, so I think either this should be 8. Yes? No. No, actually, for some reason, So this is incorrect. Yeah, this is incorrect. This formula is incorrect. This formula is incorrect because it doesn't take into consideration that I can't get this array in one operation. Okay, I get it. I get it. So what is the right answer for small case? Okay, I think what we need to understand, so in case of some k, yeah, let's fix some k. Oh my god. Okay, let's again solve the problem for k equals 1, because I did it incorrectly actually. What's the possible answer for k equals 1? For k equals 1, in principle, we could... Okay, what we really need is just an element from which there are at least k to the left side and k to the right side. Why is that? Because let's just remove some elements. Let's just take out some elements, k here and k here. Now, we have a correct answer, but the only problem is that the middle element is not in the middle. But we can easily fix that, because, for example, this middle element... So, for example, we have two elements, sorry, we have two elements like this, and they are neighboring, and they are both taken. Instead of that, we can... So if we took this element, we can swap them, and now this is the middle. If this is this element, we can swap these two, and now this is in the middle. So we only need... So actually, the question is, can you take... So the question is there an empty element such that there is at least k elements? So there should be non-taken elements such that here we have at least k taken elements. So how many ways are there to take an element to take a sequence such that there is an element for which there are at least k elements here and at least k elements here? Okay, assume that it is impossible. This means that all elements except the first k and the last k, the first k minus 1 and the last k minus 1, they are a single block. So there are k minus 1 elements in the beginning, k minus 1 elements in the end, and everything else is a single block. This means that we just need to choose from n elements 2kl such that these middle elements are a single block. So how many elements are there? There are 2kl minus 2k minus plus 2 elements. So we have made 2kl minus 2k plus 1 glue-ups. So let's subtract them. So now we have n minus 2k l minus 1 choose 2k minus 1 elements. Okay. So we need to consider all possible ways, which is n choose 2kl, and subtract the bad ones. That's it? Okay. So I don't understand what I'm missing here. So let's just comment everything out. So we have an answer. Let's go through all numbers from 1 to k for all numbers j for all numbers j. So we have ij elements. Okay, let's use k and l because it's easier for now. So answer k minus 1 is sum modular m of answer k minus 1 and something. So what is answer? What is something? Something is difference of two chooses. We need to choose from n elements 2kl, and we need to choose from n minus 2kl minus 2kl minus k minus 1, and from this number of elements we need to choose 2k minus 1. Okay, now it's a bit better, isn't it? Wow, it's not bad. Unfortunately, I feel like it might be too much because we have n log n here operations. And we have 3 seconds. Okay, maybe let's try. Maybe it's tail, I don't know. Wrong answer on processed 11? This definitely means that, oh my god, I have not enough choose. I have 1 million here. Ah, I have 1 million here. No, what? I have 1 million here. What's wrong? Ah, maybe I need more than 1 million. So I need to put 2 million? Is that it? Maybe yes. Maybe I just needed to put 2 million here. Unfortunately... Oh, this is bad. I need to remove the slow solution from the previous problem, of course. Well, it's sad, but let's try again, maybe. Right, test passed. Okay, we have 1 hour and we have a problem, the problem F. Formless is so fast. And he solved it in 7 minutes? Dude. For an array B of m non-negative integers, define fb as the maximum value of maximum minus minimum. Okay, this OR simply means that we remove all these bits from both numbers. Or not. Yeah. So let's just remove all bits of x from all numbers, and after that we just subtract maximum and minimum. You're given n integers, n and q. We start with an empty array A. Over all possible non-negative integers. Ah. Ah. Well, it's interesting now. Well, I like it. This should be not a very hard problem. So we have a number A. What? We have what? So first things first, we need to only look. I think. Oh my god, n is at most 2 to the power 22? Are you nuts? Just it's guaranteed that 0 is at most v and v is at most is less than n. It's also encrypted. Why is it encrypted? Okay, I need to do it online. Okay. Okay. So we have several numbers. Let's store. So let's take the maximum bit, which is somewhere 1 and somewhere it's 0. After that, among all these numbers, let's find the maximum bit, which is somewhere 1 here and somewhere 0 here. After that, let's again find the maximum bit, which is somewhere here 1 and somewhere here 0. And again. And we need the difference of these two numbers. Okay, what happens when we add a new number? So if it has the leading bit somewhere here different from what we had here, then we have to recalculate everything. But it shouldn't be very hard. So actually here we're interested in AND of all such numbers, and here we're interested in OR of all such numbers. So we can have this OR and AND pre-calculated easily. Okay. So let's do the following. So first of all, for each bit, we store 1 if it is different for some two numbers. Since then, here we only consider numbers which have this bit as which has this bit as 1, and here are numbers which have this bit as 0. After that, we find the first bit, which is here 1 and here 0. We can simply store the OR of all such numbers and AND of all such numbers. Okay, and starting with this bit, we store here all numbers which have two ones here and all numbers which have two zeros here. Then again, we find the first number, which is 1 here and 0 here, and so on. So how do we need to store it? I think we just need to store it as the answer. We have simply the answer. Is it enough to store the answer? I think maybe yes. Maybe it is enough. Okay, now, so let's assume that answer is something like this. So what can we do then? No, not on the answer. Let's also store all these numbers. Store the OR of these numbers and AND of these numbers. So actually we store OR of all good numbers and AND of all bad numbers. Or even to put it another way, we just store the number which we have here and the number which we have here. We just store these two numbers. Okay, let's add one new number. So we have some good positions where it is 1 and this is 0. Let's go from right to left. So if it has somewhere here 1 where both of these numbers have 0, so number A has here 1 where both of these numbers have 0, then we say that now no, we have a problem maybe. So let's look at such two numbers. Let's look at number 1, 1, 1, for example, and here we have 0, 1, 0, 1, 0. So the difference of these two numbers is, you can see what is this difference. This is 1, 1, 1. Okay, but now here we have two zeros and we added number 1 and a lot of zeros. Ah, actually this means that we need now to find the first one. So here all these numbers are equal. So if we have here some other ones, then this is fine. But now we're interested in this bit. So if this bit is 1, then we definitely have to only take these numbers. And if this bit is 0, then we're still fine with both of these numbers. Yeah, what I want to say is that now we have these numbers as zeros. So we're interested in okay, I see what can be a problem. So maybe we have a 0 here, but a 1 here. And that is really bad. Because now we want to subtract from this number. Yeah, because we get 101000, but here we get only this number. So, okay, come again. Let's assume that we have a number, new number, which a leading bit, 1. This means that now all our numbers which are left here will be some of them, one of them will be a small number. So first of all of them have 0 here. Now we need to find the first bit where here is 1, but here is 0. Okay, we can find it in some time. Then again, we have some 1 and some 0 here. Only among these numbers. So the hard part is that here we only have zeros. So here it doesn't matter what is here. It doesn't matter what is here. Hey, the question is can it be true that we have two numbers a and b, but if we have a new number c, that we need to choose some other number d? Can it be true? I think that yes. For example, let's assume that we have 1, 0, 1, 0. B is 0, 1, 0, 1. And also we had 0, 0, 1, 0. So this is definitely A. This is definitely B. But now we have a number C, which is, for example, 1. And this is D actually. 1, 0, 1, 1, 1, 0, 0. So now this is the maximum number. And since this is the maximum number, then this should be taken. So I want something to be monotonic, but I can't find what it is. And I think that I don't have any chances to solve problem G, for example, because it always takes quite much time, even for these people who are legends. Well, geothermal spent half an hour, but I will spend more because I am a slow writer. What is that? Ah. Okay. So we add some numbers. We have a so we need to store something about our set. Well, definitely. Okay, is there something which always increases? Actually, there is. This answer always increases. So assume that we want to check if our answer can increase. So first of all, okay, if the leading bit of this answer increased, then we can easily recalculate everything. So it's fine to do it 22 times. But we cannot do it, for example, 2000 times. So what after that? So assume that the leading bit is the same. Yeah, so either all these leading bits are the same. This means that actually either this number has a 0 here and it goes down, or it has a 1 here and it goes up. Okay, but is it true that this number can change because of that? Is it true that this number can change? I don't know, but of course it can. Of course it can. For example, we have number 1, 0, 0, 0. For example, 1, 0, 1, 0. Here we had 0, 0. 0, 1, 0, 0. And for example, also we have let's write like this. So the answer is 1001, but we also have this number, but it has no use here. So this is our choice, but if somebody adds us this number, yeah, so this is our choice, and answer now is 1001, but it can become 1100, and only if we take the other maximum and the other minimum. Okay, is it true that if we chose some number, then we decided not to take it, but then we again decided to take it? Is it possible? Yes, it is possible. So I think that we need to make the following. We have a set, and we need to answer, is there a number which has these ones and these zeros? And for the rest of the digits, it doesn't matter. So we need to somehow answer on such queries. Is there a number which such ones and such zeros? If we could do it in like log square time, for example, it would be nice. Or better, log time. Okay, in 22 questions. Can we do it? Is there a number with such a mask? Also, we need to somehow update it, and it's not very easy to do. Okay, for now, let's only answer about ones. So assume that we have a question. We have several ones. Is there a number with such ones? We can store it as a binary array. Yeah, we can store it as a binary array. We just, for each number, store if there is such number in the set. Okay, but this is 2 to the power 22, and here we have 3 to the power 22. Yeah, definitely. Well, but 3 to the power 11 is not that many. It's not that much. Yeah. It's sad, but I think I will not be able to solve this problem. I really don't have any idea what to do. So we have some set. We know something about this set. But we don't know enough about this set. Okay, maybe we just need to store our numbers in a set. Yeah. Okay, let's try to store our numbers in a set. Set of int. So again, if we have a number with change leading bit, we can recalculate everything in linear time. It's fine. Okay. Now let's assume that it is not the case, and we cannot do it. So we know that we have 1, we have 0, and our number, for example, is 0 here. Then let's look at this bit, and let's check if there is a number. So if here we have, is it true that we have somewhere here 1, but somewhere here 0? Is it true that we have somewhere here 1 and somewhere here 0? Also, if so, we would like to find this number. Yes? Okay, if we have a 0, if you have a 1 here, then it doesn't matter. We go forward. If we have a 0 here, then we're asking if there is a 1 here, if there is a number with 1 here. If there it is, then we are happy and we recalculate. How do we recalculate? Again, we find a 1. We go forward. So we just need to find the best number in this set. The problem is, if we have a 1 here, and here we have only zeros. Okay. So if we have a set, we can do it in several lower bounds. Yes? There is one more problem. Maybe we have... If we have a 1 here, and here we have zeros and 1s. This is a problem. If we have zeros and 1s, then we just skip this bit, but after that we cannot for sure find all numbers in which this is 1, for example. We cannot do it because it's not one lower bound in set, it's 2 lower bounds in set. And if we have a lot of such zeros 1s here, then we have 16 lower bounds. Gosh. Okay. Okay. What can we do? What can we store, actually? Well, we can store a... So in the data structure again, which quickly, it's like try. Yeah, for example, we need 0, then y, so it's a binary try. But in some moments, sometimes we are not interested in this bit, and we still need to go, for example, in all zeros at some moment, at some point. So, like in parallel. But the try cannot do that. Can it? It cannot. And we need it because it might be that this is a small number. For example, we have added some big number, and here it has 1. Here it had zeros, so we didn't bother about these bits. But here it has 1, and we want to find out if we can increase the answer. Oh. Okay, assume that the answer is something like this. So what do we need to increase the answer? If we have a 1 here, we definitely need a 1 here or here. So if we don't have it, we can simply stop the algorithm, continue with the next number. So assume, moreover, actually, notice that if we have a number if we have this answer, then all numbers in which these are zeros, they are useless instead, except our answer. So, except our answer, all numbers. Can we just store like the set of all useful numbers and hope that it's not very big? No, what? Can we? Actually. Can we store just the list of all useful numbers which can be in the answer? No, we cannot. We cannot because assume that we have all numbers with exactly 11 ones. Yeah, so we have like 20 digits, and here we have all 10 ones. Here we have all numbers which have exactly 10 ones. So there are a lot of them. How many of them? 20 factorial divided by 10 factorial divided by 10 factorial. And with 11, it's even more. Okay, a lot of numbers. And so each of them can be useful because when we are asked about some number with a leading one, for example, it can have any ones here, for example, any 10 ones here. And what we really want to have is a number without these 10 ones. So the set of all useful numbers is actually very non-uniform. Which is, let's say, less than ideal. So again, assume that we have some structure for little numbers and for big numbers. What do we do then? We try to find in the first bit. So if it is small, it is big. If both of these numbers are if there is 0 here and 1 here, we go with 0 and 1. However, maybe it is always zeros and there is 0 and 1. Or this is always 1s and this is 0 and 1. And in this case, we like need to jump 2 digits at once. Okay, what's the problem with that? The problem with that is that if we want to add a number, let's just store for each prefix, where a prefix is either digits or question marks. For small numbers, it's always either question mark or 1 or 0. We're not interested in ones. We're only interested in zeros and question marks. So for each number, let's store. Okay, so what did I want to say? I wanted to say that if we have some number which has a lot of ones, then we only can put them in question mark sets. This is fine. However, sometimes this is not the case. And we have to put the number, if we have a lot of zeros and a path with a lot of question marks, then we have to put it into a huge number of sets. Yeah, for example, a number which is just 0, we need to put in all sets, totally in all sets. That is sad. Well, actually, I only need a Boolean value. So, like, for each prefix and for each string of zeros and question marks, I only need so again, the question, let's put the question like this. We have time, 24 minutes. Okay, I have a mask on which on these places I only need zeros. I cannot have anything else but zeros. So is there a number with this quality, with this condition? How to solve this problem? I can store the answer for all numbers, but this is slow because when I need to update it, it is very slow. Yeah, if I have a number of all zeros, then everything becomes true, but only once. Yeah? Yeah, I can actually check. I can actually check all zeros. Well, we might try it. Well, we might try it, but it will be slow. Yes? So how do we update this structure? How do we update this structure? If we have some number with zeros and ones, for example, let's look at the one structure. Yeah, so we have ones and questions. We have some zeros and ones. we check if we have this set of ones, exactly set of ones in our structure. If we have it, then we don't do anything. If we don't have it, then then first of all we try to remove the 0 and we update it. So we update everything with this question. Now we only look at the sets with this one. Then we put this question. Okay, it is very slow, but let's try it because it's better than nothing. So T and Q. Then we have vector E, size Q. What? If we of size Q, yes. Then vi ans equals find ans, and we print what do we print? We print ans I it should be Q and find ans and E. Yes? Why is E yellow? So ans of size Q, then we return ans. And also we have int last equals 0. Int query, which is f equals ei. In the end, we will find int current ans. We will say that last equals current ans, and ans I also equals current ans. And here we say that ei, we have sum of ei and last modular n. And we need to add this number f. So for that we have a vector bool of ones Okay, I think we need to make n a power of 2. So let's say that const int n equals n, while n intersects with n minus 1, n equals n or n minus 1 plus 1. Okay, n is now a power of 2. So now we have VB1s of size n and zeros also of size n. This means if we have a number with these ones and other digits are arbitrary, and zeros says if we have, I think, with these zeros and other digits arbitrary. So assume that we did it. Now we can calculate the current answer. So how do we do it? Also, let's say that constant k equals what? So n is a power of 2. So what is k? K is when we take built-in count leading zeros of n and 31 minus that. Yes? My computer is burning. It's funny. Okay, so let's go from int j equals k minus 1. J is at least 0 minus j. So what do we do? What do we do? So, and also we have some current answer. We have some current answer. So we are asking, yeah, so assume that we have some current answer and we are looking at digit j. We're looking at digit j. So if we have these ones and these zeros, we are asking, is it true that there is a number in which this is a 1 and this is a 0? How can we say it? So we need to take current answer. We need to take current answer or 1 over j. So this is where we should have the ones. So if ones of these and zeros of something else, then car ans or equals this thing. Okay, definitely. Let's think what do we want about zeros. We want zeros on the same positions where we have here ones, and also we want and also we want a 0 here. It's excellent. Okay. So now we only need to add the number. So it shouldn't be hard. So let's write a function. Auto add number. Add number like to ones, for example. Int y. So what do we do? If this number is already here, so if ones y, then we just return. Otherwise, we need to say that once. Let me think. Else we need to do the following. We need to iterate over all ones in this y. So int temp equals y. While it still has ones, let's say that int digit equals temp let's say temp and temp minus 1. This is different from temp in one digit, so we need to XOR it back with temp. So now we have one digit. Now we need to, so it's function void int add number 1 equals this. It doesn't know what a function. So we need to add number 1 to y XOR d. That's it. Okay, and in the end we say that once y equals true. Okay, it's almost same for zeros. But okay, let's do it exactly the same, but we need to input not y but something else here. Okay, what do we need to do here? We need to add number 1 of f and add number 0, but not of f, but of n minus 1 XOR d of f. Yes. Okay, we have 10 minutes to debug it and to get our TL. Answers of size 1. Why? Answer of size q, where q is 2. Sorry. Again. If once y then return, why are you... Ah, here it should be the same thing. Zero 2 0 2 3 5. Yes. Maybe it's okay, but I think it's TL. Moreover, it can be WA. No, it's not var. I'm feeling hope. What? So this was the solution, and even in less than a second? Okay, but, well, I don't have a proof at all. But I'll take that. Warmness, you're breaking my heart. Oh my god. Problem H. Yes, it only requires 22 minutes. Yes. And I spent this much time on problem D2. Okay, I had several duels today, but I lost everyone. I lost just everyone duel today. Oh my god. I lost every duel. Well, if hacks were possible, I could make some hacks. But I'm pretty sure this is not the case. Well, I'm too old. I'm becoming too old, guys. New generation is faster than me. Old generation is also faster than me. I am somewhere in the middle of trash. Well. Oh my god, Sava. What are you doing? Are you leaving? If it gives... Oh my god, he is leaving International Master. It's me, in case you didn't recognize me. Well, why did it happen? So what did I do wrong? So I definitely just solved problem F's too slowly, yeah? Yeah, I solved problem F too slowly, but I also solved problem E too slowly. And I solved problem D2 too slowly. However, it was kinda okay how I solved problem ABC. D2, D1. So these 4 problems were satisfactory in terms of speed. However, this is a disaster. What? He isn't going to get so many points for this round, is he? Why 879? Oh, I even forgot. I need to make an editorial for you. Editorial, okay. Okay, I will make an editorial for you. Maximize the score. Maximize the score. You have 2 n-positive integers. You feel very bored and you play a 1-player game. So you start with a score of 0 and you take 2 integers from the whiteboard, you erase both of them and you add minimum of them to your score. After the n moves, you get 0 on... you get no numbers on the whiteboard and you get some score. You need to maximize your score. So, first thing first, it definitely makes sense to sort the numbers. So, if you see something with what doesn't like require some position, so like assume that you have these integers in some array. Actually, you're not interested in the order in this array. So order can be arbitrary because when you choose 2 numbers, nothing is depending on the indices of these numbers. The score also doesn't depend on it. So if you shuffle the numbers anyhow you like, nothing changes. So it makes sense to sort the numbers so that it will be more convenient for us. Okay? So after that, let's think, what's the maximum number that you can get? You cannot get to a to n because it should be minimum of 2 numbers. There should be something else. However, you definitely can take this number because it is at most this number. Well, formally, if these 2 numbers are equal, then you can get to a to n. But since they are equal, we can as well assume that we took the left one. So let's assume that if we take a minimum of two numbers and they are equal, then you take the left one. In these terms, you definitely cannot take a to n, even though it can be equal to some other number. Since you take always the left of them, you cannot take a to n, but you can take a to n minus 1. So this is the maximum number that you can get. What is the second maximum number you can get after taking a to n minus 1? This is actually a to n minus 3. Yeah, still, you can repeat the same process. After these two numbers, you can take these two numbers and get these to your sum. And if you continue this process, you will get all numbers with odd indices. So a1, a3, a5, etc. a to n minus 1. The question is it optimal? Or we could get some bigger answer. I will prove that actually it is not possible. So you always get at most this sum. To prove that, let's assume that there is some optimal way to do it. There is some optimal way to do it. So it takes, first of all, it takes ai1 plus ai2 plus etc. plus ain in some order. Notice that if you change the order of the operations, it is always correct thing to do. Yeah, for example, if you firstly chose these two numbers and then these two numbers, you can as well firstly take these two numbers and then these two numbers. It is a correct permutation. So you can assume that you make the operation in such an order that this sequence is decreasing. So we have our sequence, which is all odd indices decreasing. And we have an optimal way of doing it, in which there are some indices which are also decreasing. Now let's prove that I1 is at most 2n minus 1. It's obvious. You cannot get I1 equals to n, because that would violate the thing that we said. Yeah, we cannot get to n cannot be the minimum of two numbers. Let's prove that I2 is at most 2n minus 3. This is also obvious. Why is that? If it is not the case, then I2 is at least 2n minus 2. Yeah, so we have a to n minus 2, a to n minus 1, and a to n. Notice that here you have both numbers I2 and I1. But notice that there are only three numbers. Notice that each time when you take a pair, so you take minimum of a and b, you take minimum of some number ai and some number aj where j is greater than I. So in each operation there are two numbers in which the minimum ai you take to your score and aj is some bigger number. So there are ai2 and I1. Then there are also j1, which is at least I1, and j2, which is at least j2, I2. So in this area there should be at least 4 indices, but we have only 3 only 3 available to us. Generally speaking, let's look at ik. Yeah, so we have a to n minus 1 plus a to n minus 3 plus etc. plus a to n minus plus 1 minus 2k. And here we have ai1, ai2, etc. plus aik. So let's prove that ik is at most 2n plus 1 minus 2k. For that, assume that it is not true, and then assuming the contradictory thing that ik is at least 2n plus 2 minus 2k. Then let's look at all these indices. 2n plus 2 minus 2k, 2n plus 3 minus 2k, etc. 2n. How many indices are there? There are 2k minus 1 indices. However, in this set, there should be all indices I1, I2, etc., ik, and also the corresponding maxima. So each I, j in this list, it was in pair with some corresponding maximum. And since the maximum is at least the minimum, these indices should also be somewhere here. So actually there are, in this list, there are all these 2k indices. And since 2k is greater than 2k minus 1, this is a contradiction. You cannot fit all these indices into this set. So this is the proof that actually you can do it greedily. You can always take just the maximum odd index which is available. That is, you can just sort all elements and take the elements with odd indices and sum them up. You can even do it in integer, because as far as I can see, even if you sum up all the integers, you still get at most 1 billion. Let's go on. Problem B, permutation printing. Find the permutation P of length n such that there do not exist two distinct indices I and j, such that pi divides pj and pi plus 1 divides pj plus 1. I think there are a lot of different approaches, but I used the following approach. Notice that since we have a permutation, all numbers are different. So pi is not equal to pj, and pi plus 1 does not equal to pj. So let me write the statement. Find a permutation such that there does not exist indices I does not equal to j, such that pi divides pj and pi plus 1 divides pj plus 1. So there does not exist such indices. So since all numbers are different, actually this means that pi is less than pj, and this means that pi plus 1 is less than pj plus 1. Okay? Well, the problem is I can find you the permutation in which even this is false. So you cannot find two indices I and j such that pi is less than pj, but pi plus 1 is also less than pj plus 1. And for me it was quite intuitive to do. What I did was take the following array: 1n, 2n minus 1, 3n minus 2, 4n minus 3, etc. So definitely it covers the whole set of numbers from 1 to n. Now let's prove that this is true, that you cannot find two such indices. So we will prove that if pi is less than pj, then pi plus 1 is at least pj plus 1, and that will contradict this thing. Okay? Well, there are two cases. How did we get these two indices? First of all, if they are taken from the same parity. For example, they are taken from the odd parity, 2 and 4. Yeah? So pi is less than pj, where I and j are odd. Since on the odd places numbers are in increasing order, this means that I is less than j. But let's look at pi plus 1 and pj plus 1. Notice that now I plus 1 and j plus 1 are even. Yeah, so they are on even parity. And on even parity, numbers are decreasing. N, n-1, n-2, n-3, etc. So here we have two even numbers. So since I plus 1 is still less than j plus 1, this means that pi plus 1 is greater than pj plus 1. And we get it. We have it. The same thing is true if you take even numbers. So if you have even numbers I and j, this will mean that I is greater than j. That will mean that I plus 1 is greater than j plus 1. But they are this time odd. And since they are odd, this means that pi plus 1 is greater than pj plus 1. It's true for odd numbers that the order of indices is the same as the order of elements in the permutation. Okay. The second case is that I and j are of different parities. And here we have the second beautiful property of this array. The property is that all numbers on even indices, on odd indices, they are smaller than the numbers on even indices, because we chose them in that way that each number, so like all numbers on odd indices are something like not more than n over 2, maybe plus 1, I don't know, odd indices, and even indices are at least are greater than n plus 1 over 2. Yeah, so actually all numbers on odd positions are less than all numbers on even positions. Since it is true, so if pi is less than pj, so let me write pi is less than pj, and I and j are different parities. But this means that it is mandatory that I is odd and j is even. This will lead to the following, that I plus 1 is even and j plus 1 is odd. And that implies that pi plus 1 is greater than pj plus 1. Because again, all even positions have numbers which are greater than all numbers on odd positions. So this is not very hard constructive problem. Problem C. Lexicographically largest. I think some sample changed. Yeah. Not sample, but nothing very important. So we have an array A of length n and a set S. So we take an index I such that I is between I and 1 and A. We insert AI plus I into S and we delete AI from A. We want to, after that, to sort S in decreasing order and find the lexicographically largest array that we can get. So the first priority is to get as big maximum as possible. The second priority is to get, so if there are several ways in which these maxima are equal, then we're interested in maximizing the second maximum, and this second maximum cannot be equal to the first maximum, because it is not a multiset, and if we have two equal elements, then they are both removed. And etc. Notice that actually the problem is not the same if we have a set or a multiset. To prove that, let me think. For example, let's assume that we have an array 5, 4. Then the obvious thing to do is to take, first of all, this element, and it becomes 6. And then we take this element, and it becomes also 6. And if we had a multiset, this would be nice. However, we have a set, so we have just 6. And then we have an array 6. Instead of that, we could do the following. Instead of that, we could start with this element, and we could get 5 plus 1, 6. And then we could get 4 plus 1 is 5. So we have a set 5, 6, and we have an array 6, 5. And this is lexicographically larger than this, although the elements were smaller. The problem is we just need to avoid equal elements. I'm quite tired to prove you my strategy, but I will explain my strategy, what you should do. Okay, maybe I will try to prove it, but for now I will explain it. So first of all, notice that if you just take all elements from the right position to the left position, then each element gets added its index. So let's do that initially. Let's just, instead of looking at our initial array, look at the array in which we have added the index to each element. So now we have some new array. Let's call it, for example, D. So D1, D2, etc. Dn. This array is now works like follows. So when you take an element out of it, you don't add the index to it. You just add this index, you just add this element to your set. But after that, all these elements are decremented. Okay? We just decrement all the elements to the right of this element. Why does that happen? Because in the initial statement, when you remove the problem, you don't decrement the element, but you definitely decrement the indices which are added. And you only decrement them for the elements which are to the right of this removed element. Okay, so this is the problem. And what is actually astonishing maybe in this problem is that you again, as in problem A, you don't care about the order of these elements. So actually, if we shuffle now these elements, the answer stays the same. So first of all, let's explain what is the maximum possible answer theoretically. And then let's explain how to get it. So first of all, if we want to maximize our lexicographic set, we definitely want to take the biggest element as possible. And the maximum possible element is just the maximum of this set. And we can take it. So let's, for example, let E1, E2, etc. En be the sorted set. Then you can definitely get En in your set. Okay? After that, you definitely want to get En-1, but there is a problem. En-1 can be equal to this number. Let's actually write it like this. So we will get the set. Okay, I think I will do it in the other way. I will sort them in decreasing order. So E1 is at least E2, etc. is at least En. And I will say that we get the set A1, etc. And okay, first of all, A1 is E1. We just take the maximum. What is A2? We would like to have E2, but we cannot, because if E2 equals E1, then you cannot get both of them numbers, both of these numbers, and E2 is removed. Well, if you just remove this number, it's strange, because instead of that you could take E2 minus 1. it's not the best thing that you could have hoped for, because you wanted e2, not e2 minus 1. But if you take e2, then it will get removed. And if you take e2 minus 1, maybe it will not get removed. So you got to choose. And definitely the best choice is to take e2 minus 1. Maybe it will also be removed. But let's assume that it will not be removed, but something else will be removed. Yeah. So for example, if a1 is 5 and a2 is e1 is 5, a2 is 5, and e3 is 4, then we take 5. We take 5 minus 1 is 4, and then if we take e3, then e3 is removed and not e2. So we always take e2 if we subtract 1. So a2 will be a minimum of e2 and a1 minus 1. Okay, what about a3? Actually, there are the same considerations. If e3 is less than a2, then you can take e3. And it's the best thing you can do. But if e3 is equal to a2, or even more, sometimes it's more, you cannot get a number which is more than a2 or equal to a2, because you will just get a repetition. And instead of that, you could avoid the repetition by taking minimum of e3 a2 minus 1. Okay, and so on. Actually, and so on. You continue doing it until you get like an, which is minimum of en and an minus 1 minus 1. Okay. So now we actually, if we want the completeness, we would like to prove that it is this answer is achievable. So you can yield this answer by some sequence of operations. Let me think if I can prove it. Well, I guess maybe I can. So let's take these elements one by one. Let me think. Let me think. Okay, I think I know what to do. I think I know what to do. So we will construct our strategy as you will see. So assume that we have considered first I elements. Then they are corresponding to these elements, e1, e2, e3, etc., ei. Then there is a strategy which does the following. First of all, it somehow works on these numbers, and then it removes all the rest of the numbers. And each time when we remove some number, and when we remove these numbers, we get in total the same sum as here. So again, the statement: for each prefix of I positions, I can find these numbers e1, etc., ei here, and I can find a strategy which removes them first. So the first I operations is removal of these numbers in such a way that the sum of the answers, the sum of the scores after removing them, is the same as here. We'll prove that by induction, and the base of the induction is the case I equals 0 when we don't remove anything and we get the score of 0. Now let's prove the induction step. Assume that we found the strategy for these numbers, and then we need to look for the strategy for ai plus 1, which is like this. Okay, so here we have some ai plus 1. So what would we like to do? What would we like to do? So let's just apply our strategy. If we just apply our usual strategy of first removing these nice elements, then it might be then there might be some troubles. Yeah, for example, because so it's minimum of ei plus 1 and ai minus 1, and it is ei plus 1 minus some number k. Yeah, the problem is you didn't want to remove okay, I think it's technically correct. I understand. So actually it's not true that you will always subtract key exactly from this number. Maybe you will redistribute these minuses, and you will subtract it from something else, and from this number you will subtract less than key, or maybe more than key. Not sure. No, definitely not more than key, but maybe less than key. And sometimes you don't want to subtract anything at all. Sorry, but I really don't know what to say. Well, I could make some proof. Well, for me, this fact was intuitive, so I didn't prove it. I think that I will not be able to explain it to you more understandable than if you read it from editorial. But in the editorial, this proof is checked, double checked, and it should be in readable format. In my case, I might be able to make some proof, but it will be non-optimal. I think you better check the editorial. Okay, since we have this fact, all you need to do is calculate these numbers, and this can be done in linear time because I just have written all the formulae. So you sort all numbers ei in decreasing order, and you calculate this minimum. Constructive algorithms. Indeed, they are. So did somebody fail the system testing? Probably not. Probably not. Okay, problem D. Problem D was quite a nice problem. Again, I don't have a proof. Or do I? Okay, I will explain it to you in a moment. Okay, so what is the statement of this problem? We have got a pattern. We have a pattern P, which is the binary string. We say that as another string Q satisfies this pattern if for each element I there is a substring which contains this element I, such that this 0 is the mode of this segment. Mode is an element which is not rarer than the other element. So if you have two elements which occur the same number of times, then they are both modes of this distribution. However, if one of them appears more often than the other, then only this more often value is the mode of this array. So you need, so Q satisfies this pattern if for each position I there is a segment in for which this element opposed to this position is a mode. You are given a string, then f of p is the minimum number of ones in such Q which satisfies this p. And what you need to do is to find some f of s where s is a substring of p. So this is our function which we need to find. So for each substring of p, we need to find the minimum number of ones in Q which satisfies this pattern. And we need to sum it up, and the sum should be output. So first of all, we have an easiest task, which can be solved in n cubed times log n. Yes? Yeah. And then we have a hard task, which can be solved in n log n time. Okay, I am not sure if log n is needed. Let me write like this. I think no log n are required. Yeah, so O of n cube is an easy task and O of n is a hard task. Let's first of all work with this one. And again, this will require an interesting fact from me, that actually, let's calculate g of s. G of s is the following. You have a pattern s, and you say that Q, now we say that Q satisfies this pattern very well. Yes, Q satisfies this pattern very well if for each one here there is at least one here. So either this one, or this is one, or this is one. And if we have zeros, then at least one of these three symbols is 0. Okay? Then we say that Q satisfies pattern very well. And again, G of S is the minimum number of ones in a string which satisfies this pattern S. Note that if a string satisfies pattern very well, then it just satisfies this pattern. For example, assume that we have some 1, and we want to find a segment in which 1 is a mode. What I want to say to you is that you can just take this one or this one. And you can do it because at least one of these three elements is 1. This means that actually at least one of these two segments is a segment of length 2 with 1. This means that this segment has a mode 1, so segment is good. This segment is good, and for all indices you will find such segment of just size 2, so you satisfy the pattern. So since g of s is a minimum among a stricter condition, you get that g of s is obviously at least f of s, because here you consider all possible queues which satisfy pattern S and minimize. And here you only consider such queues which very well satisfy this pattern. And since they satisfy this pattern very well, there are less of them, maybe. And minimum is taken among a smaller set, thus it might be bigger. It might not be smaller, but it might be bigger. Well, the crucial fact, the crucial observation is that actually they are equal. So you always need to take. So it is enough to always so for each one if we just put for each one we put some one in one of these three positions and we minimize the number of ones, this minimized number will be the same as if we require this strange condition about modes. Well, if in the previous problem I even had any idea about how to prove it, in this problem I don't have any idea. I don't know what to do. I know what to do, I don't know how to prove it. Think sell, nice company, made a round. You'll like the problem set. Actually, this was an enjoyable problem set. I even solved problem F. So I really don't know how to prove it, but if you only try to make this one in these three positions, then it already minimizes this function g. Okay. I don't know how to prove it, sorry, because this is a mess of a fact. The way I did it is I asked myself, what is the answer for 1, 1, 1, 1, 1? And I found the following. I found the answer where I have 1/3 in the middle, and here I have zeros. Notice that actually each element, like this one, has a mode 1 in such segment. The problem is that this 1/3 looked like somewhat random. Could it be 1/2 or 1/4? What's the optimal constant here? Actually, it is 1/3, but this is because there is one more way to do it. And the one more way to do it is to take every third one in such a pattern. So instead of 1/3 of ones in the center of this string, you can take them like this. I don't know how to explain it, but after I saw it, I understood that this problem might be able to solve greedily. Okay, when we understand that it can be solved greedily, we can write an easy O of n greedy algorithm to do it. What does it do? it's just like DP with profile. Not with profile, DP with some additional dimension. So we have considered the prefix of size I, and we have tried 4 types of strings. Strings which ends in 0, 0, in 0, 1, in 1, 0, and in 1, 1. So in each one of them, we found the minimum number of ones. Now let's consider the next digit. If it is... Actually, it doesn't matter what the next digit is, but it matters what this digit is. Because if it's 0, you can write anything here. You can write either 0 or 1. However, if after this prefix, so if it is if you have 0 here. However, if after this prefix you have a 1, then 0, 0, 0 is unacceptable, because this would mean that this 1 does not have a 0 nearby. It does not have a 1 nearby. This is bad. Instead of that, we need to take 1 here. And in all other cases, it's fine to take either a 1 or 1, 0. So how to write formulae? Assume that, for example, before this new digit we had answers A0, A1, A2, A3. Assume that we are adding a 0. What is the new A0? A0, you can get 2 zeros in the end, either in this case or in this case. So it is maximum or minimum, I mean, of A0 when you have this string and you add a 0. Or this string and you also add a 0. Okay, A1 prime is the same strings, but you need to add a 1 instead of 0 here. So you have to add 1 and the same minimum. A2 is again minimum of A2 is when you have this 1, and it's like the same, but instead of this 0 and 2 you have to take 1 and 3. Okay. The only difference here is that you cannot take 0, 0 and then again 0. This means that you are unable to use A0 here. So the only difference is that now A0 prime is just A2. Let me think. Yeah, it's just A2. The only way to have 2 zeros in the end is to have 1 here. This is the only difference in our dynamics. Everything else is the same formula. Okay, this is an algorithm which works in O of n. Also, there is some corner case in the end. Yeah, because if you have last one digit 1, then it's not possible to take 0, 0 and then 1. So in the end, if you have a 1 as the last digit, then you have to choose either I1 or A2 or A3. You cannot take A0. It is not possible. Also, you can simplify your dynamics. Actually, you never need 2 1s in the row except this one last case. So actually, you can just eliminate fully A3. You can just eliminate it fully. You don't need A3. You don't need 2 1s in a row, because if you put 1, 1, it is caused by this 1 in the string P. But then if you have this one, it is caused by this one in your pattern P. But then you shouldn't have taken it because it is covered by this one. So you don't actually need this case, and here you just have A3. So A2 prime is A3, and here also A2 prime is A3. No, A1. A1. You don't have A3 at all. Okay. Well. So in O of n time, we calculate the answer for one string. So you can just take all n square strings, and for each of them you find this with my linear algorithm, and you get O of n cube time. Actually, it's not said that you can do everything in n cube time. Let's explain how you can understand that. So you have some multitest in which you have numbers n1, n2, etc., nt. Okay? And it is known that n1 squared plus n2 squared plus etc. plus nt squared is at most 10 to the 4th power. How do you then can understand what is this sum? Actually, you can understand what is this sum. Let's, instead of that, write it like this. It's n1 squared times n1 plus n2 squared times n1 plus etc. plus nt squared times n2 here. Then you can estimate each of these n1s with the maximum value of it. So n1 squared times maximum of ni plus n2 squared times maximum of ni plus etc. plus nt squared times maximum of ni. Now you can put it out of the parentheses, so you get n1 squared plus etc. plus nt squared times maximum of ni. So you know how to estimate this one. But what about this one? Actually, it's quite easy to estimate because we can write it as follows. So it is n1 squared plus etc. plus nt squared times square root of maximum ni squared. Then you can say that instead of maximum ni squared, you just consider sum of all ni squared. So here we just say take the sum of all squares. Now you get n1 squared plus nt squared to the power of 3 seconds, which is at most 1 million. So that's why you can do it in cubic time. It's fine. Okay, in problem D2, you had to make something. You still need a greedy, and it's still like some sort of DP. But this time it's a more clever DP. So you find your answer one by one. So for each prefix, you know the answer, the sum over all substrings. Okay? So when you go from this let us think. Actually, let's think a bit. What I want to say is, so let's consider all strings Q. So we have our pattern P. Let's consider all strings Q. Let's align them with how they lie in this string. Yeah, for example, if this Qi corresponds to this substring, then we draw it like this. We draw it right under this substring. In this case, we will consider prefixes one by one, and each time we will calculate the income given by this radix in all these strings qi. So when we consider this digit, we consider all strings which go through this digit, and we will say that answer plus equals how many times it is 1 here. Number of times it is 1 on position I. If we do it, in the end we will get the correct answer. To do that, let's make a lot of greedy algorithms in parallel. So when we have this situation, for each beginning from this string, from this position, from this position, from this position, we know something about our string, which starts here. What do we need to know? Actually, we only need to know about last two digits. As I said, they can be 0, 0, 0, 1, or 1, 0. You can make your dynamics more complicated and add 1, 1, but it's not necessary. It's 3 cases are enough. Okay, when you add a new digit, there are two things that happen. First of all, your greedy algorithm for each string changes. Let me consider some case. For example, let's consider string p. In string p, here we had a 1. This means that we are not allowed for these strings to draw a 0 here. We have to write 1 here. But for these two strings, we are able to write zeros here. This means that each string which ended with 0, 0 is now ending with 0, 1. Each one which ended with 0, 1 now ends with 1, 0, and each one with, which ended with 1, 0 ends now with 0, 0. Okay, how many strings have this one added? Actually, each string which starts to the left of this position and ends to the right of this position and has 0, 0 in the end. So if you have the number of these strings is A, this is B, and this is C, it is A times n minus I, where this is the right position and this is the number of symbols here, n minus I. Okay, the same, so, and you recalculate, so now A prime, for example, which is the number of strings which have 2 zeros, is the previous C, and there's other numbers are also recalculated like this. So this is added to the answer. This is how you recalculate your dynamics in case when you have a 1 in this position. If you have a 0 in this position, it is also easily recalculated. The only tricky case is when you have some strings which end here. If you have a string which ends here, sometimes even though you write here 0, it's still 1. For example, it is possible that you had a C string which ended in 1, 0. Then in their pattern, you have here 1. So you want to write 0 here, but unfortunately in the pattern here we also have 1. Usually that would lead to 1 in this place, but we cannot have it because 1 is outside of this array Q. So instead of that, we have to fix that. It doesn't really change your dynamics, but you need to fix your answer. In essence, if you had both ones, then you need to add C to your answer. Also, if you had a 0 here, I think you also need to add A to your answer. Something like this. So, and also you need to add 1 here because of the simple string 1. And finally, you have one more string which starts here. It has 0, 0 in the beginning, so you say A prime plus plus, something like this. So this is how your dynamics works. In the end, you will get the correct answer if you don't confused between different cases, you don't do anything wrong, etc. Okay, I have two only problems left, E and F. Is my rating updated? No, it's not. I think it might be, possibly, it might be updated, but I don't know. Scanhex. Shout out, greetings to Scanhex. Wonderful, wonderful. This was not a wonderful problem, at least at first. But in the end, it turned out to be very easy, and it's strange that I spent so much time on it. This is because I maybe panicked a bit, and I thought that I was missing what was happening in this problem, but it is kinda easy problem in the end. Okay. So what is said in the statement? So you have some array which is initially 1, 2, 3, etc. n. You can make the following operation several times. First of all, before everything, you have fixed k. You have fixed k. During an operation, which you can take 0 or 1 or 2 or more, as many as you want, you need to choose 2k plus 1 elements. For example, here k equals 3. And you remove from the sequence first 3 elements and last 3 elements. We can reformulate it as follows. You can choose any 2k elements such that kth element and k plus first element are not neighbors. Because if they are neighbors, then there is no way to choose the 2k plus first element. So these should not be the neighbors. And if so, you can remove all of them. The goal is to calculate the number of possible arrays which this process results in. Okay, at first you might think that it is an array of size million, and the number of possible k's is also big, it's like 500,000, so you cannot do it independently. So for each k, you'll have to make some parallel process that calculates the answers for all k's. This was at least my thought, and unfortunately this was a wrong thought, because you don't need anything at all in parallel. There is a famous idea that if you have n functions, like n procedures, and ith of them takes constant, or not constant, but some number, divided by I operations. So you spend so much time on this procedure, and in total you have m procedures. So the last one takes n over m time. Then in total you spend n log m time. If you want to be exact, n times hm, where hm is the sum of harmonic series. Google it if you still don't know what a harmonic series is. But the point is that it is sum of reciprocals of all numbers, and it grows as slow as logarithm. So actually, even if this sum continues up to 10 to the 18, it's still like 60 at most. Not much. Well, after we have had it out of the way, let's solve our problem. For each k, we will solve it in O of n over k time. that will result in O of n log n asymptotics. So this is what we need to do. Solve each problem in O of n over k time. To do that, notice that if you made L times your operation, you removed 2kl numbers. That means that actually 2kl is at most n. And that means that L is at most n over 2k. So if you can process each L in O of 1 time, then you can process all possible L's in O of n over k time. And that is what we needed. So now we have the following problem. Assume that we have an array and we have some fixed k, and L times we made the following operation. Let's take k elements, some other k elements, and between these smaller elements and between these larger elements there should be at least one element which you don't touch. After that you remove them. So this is an one operation. You do L such operations and you need to calculate how many possible arrays are there in the end. Okay, this was quite a nice observation from me. Well, I liked it. It's not like I am praising myself, but I'm glad that I was able to think of it, because it was already a disastrous round in terms of my speed, and if I also didn't find some ideas, it would be sad, not to say worse things. So you remove KL element, 2 KL elements in total, yeah, because each time you remove 2 K elements. Which elements do you remove? Can you just remove any 2k elements? If you could remove any 2k elements, the answer would be n 2k, this choose number, 2kl. The answer would be this number. The point is that it is not this number, because when you do it, sometimes you consider arrays which are not possible to get. The key observation to understand the criterion based on which you can find out if this subset can be removed or not in L operations is as follows. So let's look at the last operation. Let's, instead of trying to make these operations, let's try to undo them. How can we undo an operation? We need to choose some k elements here and some k elements here and some element which is not touched here. Then we can just revive all these elements. After that, when we revive some other elements, we can even use these ones as the center one, as the pivot. Or pivot, I don't know, pivot or pivot, I don't know. As the center element. We can, so not only the elements which are alive from the beginning, but also which we revived. Okay. So actually, what I want to say, notice also that, for example, let's assume that we have these two KL elements. So these are some KL elements, and these are some other KL elements. If there were an element here alive, we would be happy, because actually you can just use these elements alone to revive everything else. You can just always take some k elements here and some k elements here. then again some k elements here and k elements here, and revive them one by one. You don't even need to use the revived elements as the centers. You just need one good element. The problem is that KL and KL might be in touch, so they might be the neighboring elements. So the KLth and KL plus first element might be adjacent. In this case, there is nothing to choose from here, and you are unable to perform the strategy. However, there was some last operation. So let's look at some last operation. Yeah, for example, this one removed these elements and these elements. Note that again, so we would like, if it were possible to revive them in such a way that after that the two middle elements are not adjacent, we would be again happy. Yeah, for example, let me just draw it like for it to be even number of points, because now it is odd, unfortunately. Okay, like this. So notice that now, for example, these two elements are adjacent, but we can fix that. We can take these two elements and these two elements, and now the two elements which are the middle ones are this one and this one, and they are not adjacent. There might be other elements here, and we're happy. So actually sometimes we can manipulate with this array, so we can choose which elements exactly we revive in order to fix the situation. So the fact, incredible, and which I can prove, is that you always can. So if you can just revive at least something, then you can always revive the elements in such a way that after that, among dead elements, two middle ones are not adjacent. So you can after that use this element as the center one and revive everything else. How to prove that? Let's look at one revival procedure. Yeah, it is possible. So this is the center point. These are some revived elements. Sorry for me drawing them as crosses, but I need to choose something. Okay, now let's look at all the remaining elements which are still dead because nobody revived them. Let's look at two middle ones. If they are adjacent, if they are not adjacent, then we won because we use this center element and revive everything else. So if the situation is bad, then they are adjacent. However, note that they are from some side from this red dot. For example, let's assume that they are from the right side of the red dot. Notice that since our revival procedure is symmetric, we need to have positive number of revived elements here and positive number of revived elements here. So something is revived from the right side. So let's consider two cases. If there is a cross to the right side of this thing, let's consider the leftmost cross. I think we need to draw it a bit better. Yeah, it's fine. It's fine. So this element is revived and this element is dead. Instead, let's kill this element but revive this element. Now two middle elements are not these two because they are not both dead. The right one is revived now, but this one and something here, not exactly maybe this one, but something here maybe. This element is now definitely alive and it can revive now everything to the right and to the left. Analogously, you can prove the case when these x's are to the left. Then there are none of the crosses are to the right, then they are to the left, and then you can swap the conditions of these two. So you can you can revive this one and kill this one. And again, now this element is a good center element. It separates two middle elements from each other. So actually, if you can make at least one revival procedure, then you can revive everything on your board. So let's find out when you can make at least one revival procedure. To do it, you actually just need an element alive for which there are at least k dead elements here and at least k dead elements here. Well, it's easy to say that if it is not possible, then there is a, how it's called, I forgot the word which means going one by one. Okay, there is one integral block in which all elements are neighboring to each other, they are adjacent. And there are at most k-1 elements here, and at most k-1 elements here. Yeah, so everything except k-1 elements here and k-1 elements here is a single solid block. And you don't have any alive elements here to start the revival procedure. So let's take, so you have in total 2kl elements. Let's take the middle 2kl minus 2k ones, 2 plus 2 actually. So 2kl except k-1 to the left and k-1 to the right. As I have proved to you, if you cannot revive everything, then they form a solid block. It might be a solid sub-block of this block, but still it is a solid block. So actually we have now have a combinatorial question. We have two n elements. We need to choose 2kl of them such that middle 2kl minus 2k plus 2 of them, middle this number of them, form a contiguous, I remember, a contiguous subsequence, a subsegment. How many ways of doing that? This is quite standard idea when you need to calculate something like this. You can glue all this element together. Let's consider a new universe in which instead of, sorry, not 2n, it should be just n, where there are only n minus 2kl minus 2k plus 2 minus 1 elements. And instead of 2kl, you only need to choose 2k plus 1 elements. So you need to choose 2k plus 1 elements. Among this number of elements. Then actually, if you have chosen it here or here, I can create a bijection between these situations and these situations. How do I do it? If you give me this situation, I can glue all these elements together and I get 2k plus 1 elements here. And in total, there is this number of elements. And vice versa, if you give me this situation, I can find the middle element because there are odd number of these elements. Okay, sorry, I believe it's 2k minus 1 here. So k minus 1 elements here, k minus 1 here, and 1 element here. I choose this element and I replace it with a solid block of this size. And now we have n elements and 2kl here, and the middle, this number of them, are contiguous. So we have constructed a bijection, but this means that there is same number of these pictures as there are of these pictures. And the number of the lower pictures is easy to calculate because it is simply a choose number. It is n minus 2kl plus 2k minus 1 choose 2k minus 1. So this is what you need to choose. But this is bad situations. So among all possible n 2kl situations, we have this number of bad. So the total number is this. So the only thing left to do is to calculate a choose number in O of 1 time, and it is a standard algorithm. You pre-calculate all factorials and inverse factorials, modulo the modulus. To do that, first you find all these factorials in linear time. Then you make one modular inverse operation. And now you calculate these factorials in inverse order. So if you know 1 over k factorial, how would you calculate 1 over k minus 1 factorial? Actually, it's easy. You just need to take 1 over k factorial and multiply it by k. So this is done in linear time, this is done in logarithm of your modulus, and then you do this in linear time. So you have all factorials and inverse factorials, and now any choose number can be calculated in O of 1 time. Okay, finally we have a problem F. Combinatorics FFT. Sorry, I have no FFT here. I don't know what was supposed here, but I have no FFT. Problem F. Oh, somebody wrote a message to me. I think it is about my lost duels, because I lost the duel to Pike, to Capt, and to Orbless. I lost all duels today. Still, the participation wasn't the worst one possible. Okay, problem F. Maximize the difference. For an array of m non-negative, what is actually the time of my solution? Still less than a second. Sorry, I don't know why it works fast, but it works quite fast. For an array b of m non-negative integers, define f of b as the maximum value of this maximum minus this minimum over all possible non-negative integers. So we are given integers n and q. We start with an empty array A, and we need to process q queries. We add an element to our set, and then we need to calculate this maximum minus this minimum. Also, the queries are somehow ciphered, and this is only done to not allow you to do it offline. So what is offline calculation? If you have some data structure which can answer some queries, you can sometimes read all queries in advance, and then you somehow answer them in parallel. Not in parallel, like, I mean, you, for example, divide and conquer somehow these queries, and because of that you are able to not solve them separately and have some spare time. However, there are several ways to not allow you to do it. One way is to encrypt all, encode all queries, so you cannot answer the next query before you have answered the previous one, because you just don't know the next query. Or also you can make an interactive problem, but I see why they did not make an interactive problem, because the number of queries was 10 to the 6th power, which is huge. It's normal to read from a file, but it is not to read from an interaction. Yeah, it's not even normal to have more than 20,000 interactions. If you have so many interactions, this probably means that you will have idleness limit exceeded, Or if you're a problem setter, this means that probably you will have idleness limit exceeded where you are not expecting it to be, and where you don't want it to be. Okay. So, how to solve this problem? First of all, we need to understand what this formula means. This formula, so if we have some number A, we have chosen number A and number B. Well, the formula says that we need to choose some number X, then OR A with X and OR B with X, and then subtract them. What does it mean? If you have a 0 somehow, then you don't change anyhow these bits. However, if you have 1 here, then you put 1 you enforce these A and B numbers to have 1 here. And this leads, so notice that what you choose in each bit does not affect other bits. So you can solve the problem independently. It's easy to see that. So if you have 0, 1 and 0, and you want to maximize the difference, then you want to put here 0. If you have a 0, 0, then actually it doesn't matter. You just put anything here. This bit will not give you any good. The same thing about 1, 1. You can put anything here. And if you have 0 and 1, then actually the difference is negative. And in order to maximize the difference, you would like to put here 1 to also kill the 0. Now it's also 1, and you get 0 in the difference. Well, that means that you simply find all positions where A contains 1 and B contains 0 and subtract them. That is the answer. So we have now got rid of X. We only have A and B and some modular, not modular, but bitwise operations. If you want to somehow write it down, what is the formula? The formula is you need all bits where A is 1, but B is 0. So this is the answer. So if only you knew these numbers A and B, you would be happy. You would be happy because you could just calculate this formula. Unfortunately, it's not possible to, well, it's not obvious how to find these numbers A and B. And this is because the structure changes a lot. You can watch how I solved this problem during the contest, and I struggled a lot because there is so much happening here. For example, you have chosen some numbers A and B, but sometimes, for example, here because it has a leading bit of 1, and here it has a bit of 0. But sometimes you add a new number C, which also has 0 here. But since it's so good, it's a so good number, you have to choose another one, number D here, which also has 1 here, but it has some more convenient for these C bits. Sometimes it happens. Because of that, we are unable to store very little information. What I would like to do, what I wanted to do, is I wanted to only store A and B, and if I have a new number C, then I somehow look which of them is changed. This is not the case. I cannot do it. Sometimes the appearance of the number C invokes the usefulness of number D, and the profit of B declines. But then, after some other operations, B can again be important and return to this pair. Sad but true. So in order to do that, to solve this problem, you needed to understand which numbers are needed in principle. So which numbers you are interested in principle. In principle, so assume that you have these two numbers, 1011 and, for example, 1101101. So assume, not assume, but notice that if you chose this number as A, then you'd better chosen upper number as A, because it has more ones, not more by number, but more by inclusion. So each one which you can find here, you can also find here. And that means that there is no situation in which you would like to have this as number A, because this is better. Okay? So this means that if we like some number, it is useful for us, then all its supermasks are also useful for us. The same can be said about zeros. So for example, if we have some number 110101000 and 10000100, then this number is more useful in terms of being B, because its reverse counterpart contains more ones, and therefore it increases the answer. So again, the more zeros you have, the better. So if some number satisfies you, then also all its submasks satisfy you. I was able to find the following data structure. I don't know, I am sure that it is already known, but I don't know how it's named, and I wasn't like taught it really well. Well, maybe I was, I don't know. Okay, so for example, let's look at structure for ones. Structure for ones. For each mask, bit mask, for each mask, let's call dm equals true if we have a number v which contains m as a submask, and false otherwise. I think I'll need to make some example. For example, let's assume that we have numbers 0, 3, 5. Then an array from 0 to 8 or to 7. Then, for example, 0 is contained by number 3 as a submask. And the same is true about 1, 2, 3. 4 is contained by 5 as a submask. But 6 is not contained by any of them. Yeah, 6 looks like this, 3 looks like this, and 5 looks like this. Notice that the upper mask is not contained in any of the lower ones. Then this is 0. This 6 is not contained in any number in our set. And 7 is also not contained. So we want to have this array. The same is true for zeros. What do I want about zeros? Zeros. I want to calculate like em equals true if we have m, if we have number v which is contained in m, and false if otherwise. Okay. Okay, so assume that we have these arrays. They should be of size maybe n, maybe minimum power of 2, which is at least 10. Assume that we have these arrays. Then now, given this data structure, I can find the answer. So I will find A and B iteratively, bit by bit. Okay, let's look at the leading bit. We should ask ourselves, are there two numbers in which this is 1, this is 0? For example, this is 21st bit. To do that, we need to look into D and we need to ask it about 1, 0, 0, 0, 0. So is there any number which contains this mask? So if true, then well, let's go on. Let's now look into E. In E we need to ask, is there a number which is contained in this one? Simply this means that it has a leading 0. If it's also true, then our answer is at least the difference of these two bits. It is at least 2 to the power 21. Because we can simply take this number and this number. If not, then since now we are not interested in this bit, whatever this bit is in these two numbers, it cannot be true that it is 1 here and 0 here. So whatever this bit is, we will have it turned on in our X. So we will have 0 in this bit no matter what, because we failed to find 1 and 0 as decreased number and decreasing number. Okay, let's go on. For example, we have collected some answer. So if we found this one true and true, we add it to the answer. So answer plus equals 2 to the power I, in this case was 2 to the power 21. We add it. Okay, so assume now that we have some fixed answer. This means some fixed leading bits of answer. This means that we are only interested in numbers A which contain all these ones and numbers B which don't. And all the other bits they doesn't matter. They don't matter. Now let's ask about ith bit. What are we going to ask? We're going to ask, is it true that there is a number which is 1 here and 0 here? And it is easy. We ask, please say me something about D of current answer or 2 to the power I. And we also want E of what? So now we want here zeros and on the rest of the positions anything. So it is tilde of answer or 2 to the power I. Okay, if it is true, then actually there is a pair of such numbers. We can add answer plus equals 2 to the power I and move on. If not, we just don't add it to the answer and move on. And here we put question marks. So if we go through all the positions, we in O of log n time find all necessary bits and it is the answer. Answer is actually just the answer which we can push back into our array and so on. The problem is now we have a new number. We need to add it somehow to our structure. Since the process is very same for ones and zeros, I will only consider it for ones. Okay, so you have some array D. For each mask M, it contains all numbers which contain this mask V. Let me think. Yeah, for each M, we have true if there is a number which contains this mask. Now we have a new number V. Which numbers are affected? Actually, now all submasks of V should be true. That's it. You just need to take all submasks of V and make them true. The tiny problem with that, tiniest, is that the number of submasks of V is 2 to the power n at most. So in worst case scenario, you have to spend this many operations in total. And this is sad. But there is an amortized way to do that. So sometimes, yes, we will spend a lot of time, but sometimes you will do it fast. Okay, what can we do? Notice that if you are trying to add V to this subset and already see V here, yeah, notice that if you already see that dV is true, then actually this implies that D of all submasks of V is also true. Yeah? Because if you have a number which contains V as a whole, then you also contain this same number contains all submasks. This means that we can stop updating. It is already updated. So if dV is already true, we can stop and do it in O of one time. However, if dV is false, we really wouldn't like to immediately make it true, because this would violate this condition that if dV equals true, then all submask equals true. So we would like to consider all submasks of V and make them true, and only after that we make dV true. The problem is we still don't want to stupidly spend 2 to the power V time on all submasks. Let's do clever. Let's consider all submasks of V which lack 1 bit of V. For example, if V looks like this, then we consider the following 6 masks: 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, or 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1. And finally 1, 0, 0, 1, 1, 1, 1, 0, 0. All submasks which are different from the original one in 1 bit. In this case, when you are doing it, so let's run this procedure recursively. So we have a function f of v, add v and all its submasks into array D. If we found out that dv is false, then we consider all these submasks and run the function recursively for them. Okay? We run them recursively. Okay, after that, we can simply say that dv equals true, because now it is true that all submasks are already true, all proper submasks are already true, and we only need to make our own mask true. Of course, this can take 2 to the power n time. However, we can amortizely estimate how much it spends. Notice that if dv equals true, then we might say that we spent no time or all of one time. If dv equals false, then we spent so if we have m masks here, then we spend O of m time making these recursive calls. And after that, we make dv equals true. So at the cost of 1 O of m, we made 1 dv equals true. You might say, no, it's not at the cost of O of m, because each of these recursive calls also spent time. You would be right, but if this recursive call had its own true already mask, then it didn't actually spend a lot of time. It only spent O of 1 time, and we can easily count it here. If it is false here, yes, it will spend extra time, but its extra time can be amortized by this false becoming true. So formally, you can consider some sort of potential, and potential will be a number of truths in our table. Let me think what we are. A number of truths in our table. And you might notice that, so if we have spent some time on our structure and we had n truths, then we had some new. Okay, let's actually look at the following number. The total number of time that we spent, the total time that we spent, minus the number of truths in our table. Assume that we did our function. Now we have t prime time spent, and we have some increased number of truths. Actually, let's multiply it by m. Yeah, truths multiplied not by m, but by logarithm of n. Log n, log n. Okay? So I want to say that actually this is the left thing is at least right thing. Prime here. Let's rewrite what I want to prove. I want to prove that t minus t, t prime minus t, minus t is at most log n times truth minus truth prime. Truth prime minus truth, sorry. Okay, we want to prove this inequality. This is true because, again, each time when you had some false which becomes into true, you spend O of m time, and in total you spend O of m time times the number of false which turned into truth. This is what is said here. The amount of time you spend is at most the number of falses which become truths times log n. Okay, so this is true. So if we consider the function spent time minus truth times log n, then it always decreases. Notice that initially it is 0. Initially you have spent 0 time on your structure, and you have 0 truths in your table. It is your potential in the beginning. Then, in the end of the process, it will also be non-negative, non-positive. So this means that t prime minus truth prime times log n is at most 0. This means that time that you spend is at most number of truths times log n. But number of truths is at most n. So you actually spent n log n time on the whole thing. So this is amortized. Well, also, you like not really spend truth times log n, you also spend O of 1 times by itself. So that means that actually you spend n log n times n log n time plus, or even log n. I'm not sure, so it's either q or q log n. It doesn't matter, anyway, it's... You can write like this, q n plus q log n at most. So this is fine because you have 4 million n, 1 million q, the sum of all n's and sum of all q's is small, log n is at most 22, so in total it's not much. I was actually wrong sometime before. I said that I lost all duels today, but no, actually I declared a duel against Bashkort and I defeated Bashkort. So today is not the total failure, not the total disaster. I won Bashkort. So I did a nice job, maybe. Also, I have an increased rating. Well, it's not the worst thing in the world. The round was nice. Well, have a nice day.